This is section 8.3, complex numbers in polar form. We'll begin with plotting complex numbers in the complex plane. So a complex number has two parts. It has the real part, which is part A, and the imaginary part, which is part B. So just this B is the imaginary part, and this A is the real part. Okay, the two axes are required to represent A plus BI graphically. So as you can see, we have an imaginary axis and we have a real axis. So the real axis is the horizontal axis, and that represents the real part of the complex number. And the imaginary axis, which is the vertical axis, that's going to represent the imaginary part. And we call this the complex plane. A complex number, z equal to a plus bi, is written as an ordered pair a comma b. Let me just get that off of that writing a little bit, and can be graphed as such in the complex plane. So as you can see, 2 and then 3 along that imaginary axis. Okay, graph the complex numbers in the complex plane. So we're going to graph -1, -5. So that will be here, and this is -1 minus 5i. 3i would be 0, 3. This real part is 0. And there we have 0 plus 3i. And then we have -4. So here the imaginary part is 0. So it's -4, 0. And we have -4 plus 0i. Okay, the absolute value of a complex number, z equals a plus bi, is the distance between AB and this origin in the complex plane. So the absolute value is more commonly known as the magnitude, and you might also hear modulus, okay? You will have to know both. And so let's go ahead and use that formula, the square root of a squared plus b squared, to come up with the modulus for each of these complex numbers. So given z equals -7 minus 12i, we know that that modulus is equal to the square root of -7 squared plus -12 squared. Again, we are just taking this imaginary part only, not the I with it, okay? And so that comes up to root 193. How about 4 minus 6i? That modulus is going to be equal to the square root of 4 squared plus 6 squared, or -6, excuse me. It's not going to make a difference because we're squaring it. And of course, we come up with 2 root 13. Okay. Now we're going to write the polar form of a complex number. So the complex number z equals a plus bi. We actually say that this is rectangular form, also known as Cartesian. Now, we say rectangular form since we really are in a complex plane. The polar form, we will be using z equals r multiplied by cosine of theta plus I sine of theta. That is because a is equal to r cosine of theta, b is equal to r sine of theta, and of course we know that r is root a squared plus b squared, and we also will use tangent of theta equals b divided by a. The value of r is the modulus of z. So this is quite easy to find. So this r is going to be the modulus of z. Okay? And we say that theta is the argument of z. There are infinitely many choices for theta, but normally theta is taken on 0 to 2 pi, or of course, the angle between 0 and 360 degrees. You might see this notation. So let's talk about this. Cis stands for cosine I sine. Okay, so when you see R, cis theta, that's the same as cosine I sine. Okay, and you can see this example right here. 2 cis pi over 3. Additionally, for a real number theta, Euler's formula states that e to the I theta is equal to the cosine of theta plus I sine of theta. So for example, we can write z equals 2 cosine pi over 3 plus I sine pi over 3. We can just write this as 2e to the pi over 3i. Let's write the following complex numbers in polar form. First thing we want to note is that we are in quadrant 3, negative and negative. So this is quadrant 3, okay? So let's start with r is equal to the square root of negative root 2 over 2 squared plus negative root 2 over 2 squared. And we're just going to have r equal to 1. We have the tangent of theta equal to the opposite of root 2 over 2 divided by the opposite of root 2 over 2. And of course, that's equal to 1. So, therefore, theta is equal to 5 pi over 4. So now we can write z as the cosine. Let me move this up just a bit. The cosine of 5 pi over 4 plus I sine of 5 pi over 4. Okay. Okay. Let's take a look at our next problem. In number 7, we have z equals 12 plus 5i. So we know that we are in quadrant 1. So we have r equals the square root of 12 squared plus 5 squared. So we have r equal to 13. And we have the tangent of theta is equal to 5 divided by 12. So theta is equal to the inverse tangent of 5 over 12. And you'll come up with theta to be approximately 0.39. But we'll just use the inverse when we write that out, or the exact value when we write that out. We could write both. So we have z is equal to 13 cosine of the tangent inverse of 5/12 plus I sine of the tangent inverse of 5/12. And we could write an approximate, and that's approximately equal to 13 cosine of 0.39 plus I sine of 0.39. And that would be, you could use either one of those. And this is about 22.6 degrees. Okay. Okay, let's take a look at number 8. Write z equal to 6 cosine 135 degrees plus I sine 135 degrees in rectangular form a plus bi. So we have z is equal to 6, and that would just be the opposite of root 2 over 2 plus root 2 over 2. Well, that would mean that z is equal to the opposite of 3 root 2 plus 3 root 2i. Okay, let's talk about products and quotients of complex numbers in polar form. So we have that if we're given z1 and z2 in this form, they have their subscripts, that when we multiply them together, we have that we can add these two angles together, okay? And likewise, if we have a quotient, we can subtract these two angles. Okay, so let's give it a try. Given z1 and z2 as shown, write the product in polar form. So we can go ahead and have that z1 multiplied by z2 is going to be 20 times 3, and then we're going to have the cosine of 30 degrees plus 210 degrees plus I sine of that same sum. So that comes out to be 60 cosine of 240 degrees plus I sine of 240 degrees. And how could we also write this? We could also say that this is equal to 60 cis 240 degrees. Okay. What if we're given z1 and z2 as shown and we want to find the quotient? So we will have z1 divided by z2, and that's going to be 8 divided by 2. So we'll divide their r's, and then we'll have the cosine of these angles subtracted plus I sine of these angles subtracted. And we come up with 4 cosine of pi over 3 plus I sine of pi over 3. Now we can also write this as 4 cis pi over 3. Okay, let's take a look at number 11. We're given z1 Z1 and Z2, and now we're going to write their product in polar form. So as you can see, Z1 is in quadrant 1, and also Z2 is in quadrant 1. So let's write that down. Z1 is in quadrant 1, and we also have Z2 is in quadrant 1. So we have R equals the square root of 1/2 squared plus root 3 over 2 squared, and we'll come up with R equal to 1. Okay? And so it's going to look the same here. We have R equals the square root, and this time we'll have root 3 over 2 squared plus 1/2. And that's, again, 1. Okay, so let's go ahead and find the tangent of theta is root 3 over 2 divided by 1/2. So we have the tangent of theta is equal to root 3. And so theta is equal to pi over 3. Let's take a look over here. For Z2, we have the tangent of theta is 1/2 divided by root 3 over 2. And so we have the tangent of theta is 1 over root 3. And of course, theta is pi over 6. So now we could say that Z1 equals cis pi over 3, and Z2 equals cis pi over 6. So now, if we're going to find the product in polar form, I'm going to have to make up a little bit of room here because I wrote so very big. There we go. So now what can we do? We can say that this product, Z1, Z2, equals cis pi over 3 plus pi over 6, and that's going to be equal to cis pi over 2, and that's just the cosine of pi over 2 plus I sine of pi over 2. And actually, if you notice that the cosine of pi over 2 is 0 and the sine of pi over 2 is 1. So you could also say that Z1, Z2 is just equal to I. And I could probably move that over here, and I could get rid of, there we go. Make that a little bit smaller. Okay. Okay. Okay, now let's look at powers of complex numbers, okay? And looking at our theorem, you can see that if Z is equal to R cis theta, then Z to any power n, DeMoivre's theorem. So to any power, we would be able to use this formula here. So we will raise R to the nth power and then use that value of n in front of theta. Okay, so let's use DeMoivre's theorem to compute this power of complex numbers in this example. So we have this complex number raised to the 4th power. Okay, so let's go ahead and use that theorem. So we would say that that is equal to 2 to the 4th multiplied by the cosine of 4 times 3 pi over 16 plus I multiplied by the sine of 4 times 3 pi over 16. And that comes up with 16, and we have the cosine, and simplifying that, you'll see that that's 3 pi over 4 plus I sine of 3 pi over 4. And so we now have 16, and finding each of those, we have the opposite of root 2 over 2 plus I, we'll put the root 2 over 2 first, root 2 over 2I. And that comes out to the opposite of 8 root 2 plus 8 root 2I. Okay. Taking a look at number 13, we see that we have 2 root 3 plus 2I raised to the 6th power. And so, again, we will write this in the form of A plus BI. So we have R is equal to the square root of 2 root 3 squared plus 2 squared. And you'll come up with R equal to 4. And then we have the tangent of theta is 2 divided by 2 root 3. And that is equal to 1 over root 3. So theta is equal to pi over 6. So now, using DeMoivre's form, we have our theorem 2 root 3 plus 2I to the 6th power is equal to 4 cis pi over 6 raised to the 6th power, and that's equal to 4 to the 6th cis 6 times pi over 6. And that's equal to 409, so 4096 cis pi. And we can also write that as 4096 multiplied by the cosine of pi plus I sine of pi. And of course, we can find those values. -1, the cosine of pi is -1, plus 0I. And we come up with -4096. So -4096. Okay, now we're going to find the nth roots of a complex number. So, in order to do that, if we're given z equals r cis theta, so for an integer where n is greater than or equal to 2, z has n distinct nth roots of this form, and you can see them here. So it will be this form or this form. So let's find the 4th roots of 81 using this, and we'll just take our time here. So as you can see, we have z is equal to 81 plus 0I. And we also have that r is the square root of 81 squared plus 0 squared, and that's just equal to 81. We also have the tangent of theta. Let me see if I can bring this in a little bit so that I can fit the tangent of theta in. And we have the tangent of theta is 0 over 81, which is 0. So we know that theta is equal to 0. Okay, so what can we say? We can say that z is equal to the 4th roots of 81 times the cosine of 0 plus 2 pi k divided by 4. And remember here, this 4, let me go ahead and change this to a different color. We could use here. And then we'll divide this by 4. Then you can kind of see where those fit in. Sine of 0 plus 2 pi k divided by 4 again. And here k is 0, 1, 2, and 3. Okay, so let's try for each one of these. We'll start with k equal to 0. We have 3 cosine of 0 plus I sine of 0. And we come up with 3 times 1 plus 0i, and we have 3. For k equal to 1, we have 3 multiplied by the cosine of 2 pi over 4, and of course, that's going to be pi over 2, plus I sine of 2 pi over 4. And that's equal to 3 cosine of pi over 2 plus I sine of pi over 2. And then why don't I just mark these as pi over 2. And then you'll be able to just see that. And we can just go ahead and compute these. So we have 3, and then we have 0 plus 1i, or I times 1, and we come up with 3i. Okay, let's try k equal to 2. So we have 3 times the cosine of 4 pi over 4, and again, that's just pi. I sine 4 pi over 4. And we have 3 times negative 1 plus I times 0, and we have negative 3. Let's try k equal to 3. See if I can move these down just a bit, give you a little room. So now we have k equal to 3, and we have 3 times the cosine of 6 pi over 4 plus I sine of 6 pi over 4. And again, we have 3 pi over 2. Just makes it a little bit easier when we're computing these. And we have 0 plus I times negative 1. We come up with a negative 3i. So what do you see that we have? We have our roots are plus or minus 3 and plus or minus 3i. Okay, the last thing we're going to do is we're going to find the cube roots of 8 cosine or 8 cis 204 degrees. And we'll write the results in polar form. So we'll go ahead and begin with the cube root of 8 multiplied by the cosine of 204 degrees plus 360 degrees, all divided by, all divided by 3, plus I sine of 204 degrees plus 360 degrees, k, all divided by 3. And again, we have to define k, and here k will be 0, 1, and 2, since we're just finding the cube roots. Okay, so now let's start with k equal to 0, and we have 2 multiplied by the cosine of 204 degrees divided by 3 plus I sine of 204 degrees divided by 3, and that's equal to 2 cosine of 68 degrees plus I sine of 68 degrees. And these are going to be our roots in exact form. We now have 2 cosine of 204 degrees plus 360 degrees, because now k is 1, divided by 3, plus I sine of 204 degrees plus 360 degrees, divided by 3. And that's equal to, maybe I could make that a little bit smaller so that we could fit that in. Why I write so big. And that's equal to 2 cosine of 188 degrees plus I sine of 188 degrees. Okay, and k equal to 2. We have 2 multiplied by the cosine of 204 degrees, and now we're adding 720 since k is equal to 2, divided by 3, plus I sine 204 degrees plus 720 degrees, divided by 3, and now we come up with 2 cosine of 308 degrees plus I sine of 308 degrees. And these are our 3 roots. Okay, and that concludes this section.